Hello, hello. Let me know when you can see and hear me. Hi, 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 young Cyan. Hello. And hi, Juahe. Hi, Emily. Yeah, amazing. Hi. Who else do we have? Oh my gosh, sorry. Whoa. I was watching myself. That was so strange. Hi, Chinwendu. Hi, Marina. Hi, natural scientist. Welcome back. Okay, we're going to get straight into it because we got some work to do. I hope that you've got, hi Aria. I hope you've got your calculators ready. I hope you've got your, um, I don't know, your chemistry calculation brain switched on. That's absolutely fine, Aria. Hi Yashi. I'm glad that you have made it here, and obviously you can always catch up with that lesson at another time. Okay, so I have chosen just three titrations, right? Because we're here together for half an hour. I've chosen three titrations. Hi, Yvonne. That I think kind of demonstrate the breadth of the challenge that you could be faced when it comes to titrations. Hi, Kimia. Now, these are mostly redox titrations, but if you're in year 12, which I know a good few of you are, don't worry, it's still the same concept as our acid-base titrations that we see in year 12, because ultimately all that matters is the ratio once you've got the equation. Okay, so the number one thing that I need you to keep in mind as we're doing these calculations is, and some of you might already be able to see me leaning over to the side, when in doubt, thank you, moles. Great. Okay. Now, this is never more important than when it comes to these really crazy looking calculations. Okay. Because they will do everything that they can to make it look as scary and as confusing as possible. But if you have no idea what you're doing and you just calculate the moles, what you can calculate the moles for, you will still have a good few marks, even if you don't get to the final answer. Okay, so if you're completely lost, calculate the moles. Hi, Batman fan. Okay, I think we should. Let's make some more, yeah, when in doubt, moles and mole mandem jumpers. Okay, now when it comes to titrations, typically our calculations are going to follow a particular number of steps as our baseline. So we'll find the moles. We'll then look at the ratio between the moles of what we've got, X, and the moles of what we're looking for, Y. Then we might need to do some scaling that will make more sense when we get into our practice questions. And then we will find at the end whatever we need to find. Okay, that might be mass, that might be percentage by mass, that might be MR, that might be a number of different things. Okay, but ultimately, if we find the moles first and we follow these general steps, that will get us through a big chunk of our questions, no matter how crazy difficult they look. Okay, so are we ready for the first one? Are we ready? I need some enthusiasm. I need some enthusiasm. Okay, no problem, Aria. I hope to see you next week. Okay, that's not not very enthusiastic. Okay, young Sahab, thank you. That's better. Thank you, Sahab. That's what I'm looking for. Okay, so a solution of iron 2 sulfate was prepared by dissolving 10 grams of hydrated iron sulfate in water and making up to 250 centimeters cubed. Hi, Fahim. The solution was left to stand, exposed to air, and some of the iron 2 ions became oxidized to iron 3 ions. A 25 centimeters cube sample of that partially oxidized solution required that much potassium dichromate for complete reaction in the presence of an excess of dilute sulfuric acid. Oh my goodness. Okay. Now, when we see a question like this, we need a plan of action. Okay, so we want to start with a plan of action. If we get lost somewhere in the plan, then we just find the moles and we hope it gets us to the end. That's one question. It is 6 marks. Okay, this is, oh, just wait and see what's coming. Okay, so let's try and figure out where we're trying to get to so that we know what our plan is. Okay, yes, this is the ionic equation at the bottom for iron 2 reacting with the dichromate. So what's essentially happening is we have got some iron 2 sulfate dissolved in water, which is just going to be a source of Fe2 plus ions. Okay, that's what we've got at the beginning. So that's what we've got. And that's 250 centimeters cubed of this. Then when we leave it to stand, some of that iron 2 plus is being oxidized to iron 3 plus. So now at the end, hi, Michael. Yes, Marina, probably like 6 parts of the calculation. We're going to have some Fe2 plus and also some Fe3 plus. Okay. Once we have this sample, this is still 250 centimeters cubed. They have taken out, hi, Liam. They've taken out a small sample, so 25 centimeters cubed of that solution of Fe2 plus mixed with Fe3 plus, and then titrated that against potassium dichromate. Okay. So now we have kind of visualized what's going on. Now we can start to figure out what we need. So to figure out what do we need? What do we want? The percentage of iron 2 ions that has been oxidized. What is that? To find out the percentage of iron 2 ions that had been oxidized, what do we need? What do we need? Oh, maybe at some point, Fahim, but ultimately, the percentage of iron 2 ions that have been oxidized, yes, we can absolutely start by finding the moles of the dichromate, because that's what we've got enough information for. But at the end, again, it's helpful to work backwards to figure out how we're going to approach this. To find the number of moles that were oxidized, we should probably figure out how many moles of Fe2 plus are remaining at the end, divided by the number of moles of Fe2 plus that we had at the start. Actually, no, we don't want to do that. We want the number of moles of Fe2 plus that have been oxidized divided by the number of iron 2 plus, the moles of iron 2 plus that we had at the start. How will we figure out each of these two things? Well, we already have the moles of iron 2 plus at the start, because that's what we dissolved in our solution to begin with. 10 grams of this compound in this volume. Okay. To find the number of the moles, of Fe2 plus that were oxidized, that is going to be the moles of Fe2 plus that we had at the start minus the moles of Fe2 plus that we have at the end. Okay. Again, we already know the number of moles of Fe2 plus that we have at the start. In order to find the number of moles of Fe2 plus that we have at the end, we are going to use, I'm going to move this closer, the number of moles of our dichromate and our balance symbol equation to get us there with the ratio. Okay, now we have a plan. Now we know what we're trying to get to. So, oh, Liam, that's a good question. I'll answer that question when we get there. Okay, let's start at the beginning of our plan, which is, when in doubt, find the moles for whatever we can find the moles for. And that is, of course, our starting dichromate. Okay, because the dichromate, that's what reacted with the Fe2 plus that we had at the end. So the moles of potassium dichromate is equal to concentration times volume. Lovely, Michael. Concentration was 0.01, sorry, times 23.70 over 1,000 to give us 2.37 times 10 to the minus 4. Okay? We can now, as we've just seen, use the moles of the dichromate to tell us how many moles of the Fe2 plus we had in that solution. I'm just going to highlight it to draw your attention over here. The moles of the dichromate will tell us the moles of Fe2 plus that we had left at the end. What is the ratio between the dichromate and the Fe2 plus? What's the ratio? Lovely, Liam. Not 6-1. I'm with Liam and Jawahir, 1-6. 1 dichromate to 6 Fe2 plus. So we're going to multiply by 6. Which gives us, oh gosh, where's my calculator? Which gives us 1.422. Thank you, Michael, times 10 to the minus 3. Okay, so far, if we think back to our steps for a titration, we've done, I'm going to go back one slide very briefly. We've done moles of what we can find the moles for. We've done the ratio, we looked at the ratio to find the moles of what we care about. And then we need to often look to scale. That's not going to be in every single one, but it's typically going to be in our longer calculations. And by scale, what we mean is we have calculated the number of moles of Fe2 plus in 25 centimeters cubed. But we need to find out how many moles of Fe2 plus we had in the original sample that was sat there oxidizing. So Yashi, you are absolutely right. Oh gosh, let me section off my lovely diagram. Okay, so the number of moles of Fe3 plus, sorry, 2 plus in 250 centimeters cubed is this times 10. So 1.422 times 10 to the minus 2. Woo-woo indeed. Now we've got the moles of Fe2 plus at the end. We're going to need to subtract the moles of Fe2 plus that we had at the start. How are we calculating the number of moles of Fe2 plus at the start? How are we going to do that? Anyone? Hello? Hello? Thank you, Michael. Mass over MR. Mass of what? Mass of what? I even underlined, oh, I underlined it, didn't I? Okay, lovely. So the mass of the iron, the hydrated iron sulfate, because FeSO4, this hydrated compound, this up here, that is our source of our Fe2 plus ions. So as many moles as we have of this salt is the same as the number of moles of our Fe2 plus. So that would be 10 divided by 277.9. And so to answer Liam's question from earlier on, we don't need to worry about the sulfate and the waters because ultimately the moles of our salt to the moles of our Fe2 plus is 1-to-1. Okay, so we end up with 0.0360. Great. Oh, this is going so well. Now, to find the number of moles of Fe2 plus that were oxidized, that's going to be the number of moles that we had at the start, 0.0360, minus the moles that we have at the end, 1.422 times 10 to the minus 2, which gives us, it's 1-to-1 because in our salt, we only have one Fe2 plus ion, right? If we took our salt and we dissolve that in water, it's going to give us Fe2 plus and SO4 2 minus. So for every one of these, we get one of those. Okay. You are absolutely right. Lovely. We get 0.0218. So now to find our percentage by mass, we made it 0.0218 divided by our moles at the start, 0.0360, multiplied by 100 to give us, 60.5%. Hi, A, of course. Okay, not too bad. 12 marks. Okay, so again, and I want to remind you again, this is why this hat is so important. This is why I said this so much that my students made me a hat of this. It's because let's say you had no idea how to get there, but what you did was you decided, okay, I know I can calculate the moles of dichromate because it's concentration times volume, and I know that I could find the moles of Fe2 plus because of the ratio. Then you've got, 2 marks at least without having to do too much. Okay, so, and who did I make promise me this? Was it year 12 or year 13? I can't remember, but you all now have to promise me. I think it was I can't remember. You should never, ever, ever, ever leave a calculation question blank, especially a titration calculation. There we go. I knew, year 12. But year 13, you too, never leave a calculation question blank. It doesn't matter how disgusting the calculation looks, okay? Find the moles of something, do the ratio to find the moles of the other thing, and bank 2 marks. And then if you don't know where to go from there, keep it pushing, okay? I mean, year 10, well, do you know what? Everybody, Ashi, everyone. No blank calculations. That was my pinky promise, okay? You could get 60.6 again, depending on how you round at different stages. Okay, so if you kept everything in your calculator, then you should get 60.5, but you'll get a slight range either side. Liam, it could happen. It could happen. Okay, are we ready for the next question? Are we ready? Yeah. Oh, okay. So we have got this is 8 marks. 8 marks. But again, there are at least 4 marks available, even if you have no idea what's going on, you calculate the moles and you keep it pushing, you'll get 3 or 4 marks already. Okay, so don't let these questions panic you. Know that you're going to get some marks regardless. Okay, so try and come up with a plan. If you're like, no, my head is spinning, I don't know what I'm doing, find some moles, keep it pushing, and then if you've got time, come back to it at the end. Okay, but no blank titration questions. Okay, we have got a white solid, and that white solid contains sodium ethanodioate and ethanodioic acid dihydrate, and also an inert solid, so just a solid that's not doing anything. A volumetric flask contained 1.90 grams of this. Actually, I'm going to highlight instead of underline. Contained 1.90 grams of this solid in 250 centimeters cubed. Okay, they did 2 different titrations. So in the first, this is a year 12, year 13 calculation, but again, year 12s, you can do it as well. Okay. In the first titration, it was a titration between potassium manganate and, okay, great. So they reacted it with potassium manganate. And then in a second titration of a fresh sample, it was a titration against hydroxide ions. We need to find out the percentage by mass of the sodium ethanodiol. Okay, so 8 marks. So you should have, a good 10 minutes. Again, let's consider our plan. If we want the percentage by mass of sodium ethanodiol, what does that mean? Well, that means we want the mass of the sodium ethanodiol divided by the mass of the whole thing, which is 1.90 grams times 100. Okay? To get the mass of the sodium ethanodiol, how do you think we'll get the mass of it? What do we need to get the mass? Oh, young Cyan, we'll see where the marks come from as we start working. As in calculation-wise, lovely Gertie, great. We're going to need the moles and the MR. So that's going to be the moles multiplied by the MR of the sodium ethanodiol. Okay, now the question is, how do we get the moles of the sodium ethanodiol? That's where things start to get a bit more complicated and where we have to start looking at this question really carefully and what these two titrations are telling us, okay? So this first titration, actually, let me maybe even write this out. So in our mixture, we've got sodium ethanodiol, I'm going to write them next to each other, and the ethanodioic acid. In our first titration with the manganate, what is that reacting with? What's the manganate reacting with? Just looking at the equation. Oops, that should be a 2. Just look at the equation. What's the potassium manganate reacting with? Lovely, Yvonne. Great. The manganate is reacting with the ethanodiol ions. Okay. Now, of the species in our mixture, what's got ethanodiol ions? Of the species in our mixture, what's got ethanodiol ions? C2O4, 2 minus. What's got them in them? I mean, yes, the ethanodioic acid, also the sodium ethanodiol. Both of them have got those ions. Okay, so that means that this first titration is going to tell us where's my pen gone? This first titration is going to tell us the total moles of ethanodiol, because there's ethanodiol in both. Okay, you might want to refresh, just because I'm watching myself. I know that sounds really weird, but I'm not seeing a lag, so I'd recommend refreshing. Okay, in the second titration with a titration against sodium hydroxide, well, sodium hydroxide is a base. So what's the base, the sodium hydroxide reacting with? Yes, AN means moles. What's the sodium hydroxide reacting with? Just looking at the equation. Just looking at the equation. I'm with Yashi, so not exactly, Michael, the ethanodioic acid. So only the ethanodioic acid. So our second titration is going to tell us the number of moles of the ethanodioic acid. Okay. Again, this is not organic chemistry. This is just looking at the equation and looking at what's reacting with what. So if The first equation tells us the total number of moles of ethanodiol ions, and the second equation tells us the number of moles of just the ethanodioic acid. How are we going to figure out the moles of the sodium ethanodioate? How are we going to figure out the moles of the sodium ethanodioate? How would we do that using what we've got? Lovely. Subtraction. We'll take the total moles of our ethanodioate ions and subtract the number of moles of the ethanodioic acid. And then what's left over would be the moles of the sodium ethanodioate. Absolutely. Okay, so let's get to work. Let's get to work. Let's do it. We planned it. Let's do it now. I'm going to split my working section in half. I might even need it in thirds. Okay, so we're going to work each titration at a time. Okay, from our first titration, what do we have enough information to calculate the moles of? How do we know which way to subtract? Because if one thing is the total, one thing is both, then we have to take away the one that's just one. We can't take away something that's just one thing, and then from that, take away something that's two things. Okay, you're absolutely right. We've got enough information to find the moles of the manganate. So that will be concentration times volume. Concentration 0.02. Volume 26.5 over 1,000 is equal to something. Something. Anybody? Thank you, Michael. 5.30 times 10 to the minus 4. Then we'll use our moles of the manganate and we'll use our ratio to find the moles of the ethanodioate ions. What's the ratio? What's the ratio? Wonderful, Liam, 2 to 5. So we'll take 5.30 times 10 to the minus 4, divided by 2, times it by 5, to give us 1.325 times 10 to the minus 3. Look at us, we got 2 marks already. Okay. Remember to scale. This was the number of moles of the ethanodioate ions in our 25 centimeters cubed titration, but our original solid was dissolved in 250 centimeters cubed. So absolutely, we're going to times by 10 to get our moles of ethanodioate ions in our original solution. So 1.325 times 10 to the minus 2. Okay, that's our total moles of our ethanodioate ions. So we're going to bank this and save it for later, because now we need to use our second titration to figure out the moles of our ethanodioate acid. Okay, so first, okay, no problem, Liam. So first, we'll find our moles of hydroxide. we multiplied by 10 because in our titration, that was only against 25 centimeters cubed of the solution. But our original solid was dissolved in 250 centimeters cubed. So the original solution would have had 10 times as many moles as what we actually had in that titration. So similar to the last question. We haven't got the moles of the acid yet. We've currently got the moles of the ethanodioate ions from the moles of manganate. So now we need the number of moles of the ethanodioic acid based on the moles of sodium hydroxide. Okay, we are Jawahir, yes indeed. So our moles of hydroxide, concentration times volume, 0.1 times, oh, hang on. What's our volume of sodium hydroxide? 10.45. Hi, Alara. To give us 1.045 times 10 to the minus 3. Okay, we'll then look at our ratio to find the moles of our ethanodioic acid. What's the ratio? 2 to 1. So divide by 2. 5.225 times 10 to the minus 4. Lovely, thank you. And again, that titration, we always have to remember that scaling step. So to check for the scaling, that titration was done on a 25 centimeters cube sample. So again, we need to scale back to the original 250. Lovely. Great. So now we have our moles, our total moles of ethanodioate ions. We have our moles of the ethanodioic acid. So we can calculate our moles of sodium ethanoate. Am I going to run out of space? Maybe. As 1.325 times 10 to the minus 2 minus 5.225 times 10 to the minus 3. Yeah. Which gives us 8.025 times 10 to the minus 3. Mass is going to be equal to Mr. Moles. What's the MR? Oh my goodness. Whoa. 134. Thank you, Chinwendu. To give us 1.075. So now to get our final answer, I'm just going to put it right here up at the top. Our mass is 1.075 divided by the original mass of the whole sample, 1.90, multiplied by 100 to give us, yeah, who said 56.6% ages ago? Who was that? Amazing, Jawahir. Great. Hi. Hi, Just Aerosmith. Well done, Chinwendu. Okay, yes, indeed, Liam. Let's do a quick recap of what we've done. Okay, and our plan is up here at the top, so we can also just refer to that as we are talking about it. Okay, so we worked backwards. We knew that we needed the percentage by mass of sodium ethanoate. And percentage by mass just means the mass of that species that we care about divided by the total mass of the whole sample. Okay, the whole sample had a mass of 1.90 grams. So we knew we needed to find the mass of sodium ethanodioate. Okay, through our two titrations, we had to identify what those two different titrations were telling us. The first titration told us the total number of moles of ethanodioate ions, which are in both of our species. And the second titration told us just the number of moles of the acid. So to find out the number of moles of the sodium ethanodioate, we just subtracted our total moles, because this was our H2C2O4 plus our Na2C2O4. So then to find just the Na2C2O4, we had to subtract the total from our H2C2O4. Once we had the moles of that, then we can just plug it in. Okay, but also, and again, the nicest thing about this question, you can get so many marks without even figuring out this bit. Okay, so figuring out that you have to subtract the one from the other, that's worth, you know, a minimal number of marks compared to the number of marks that you get from calculating the moles. Okay, because if you could spot just from your general understanding of titrations, I'm going to calculate the moles of the manganate, I'm going to use the ratio to find the moles of the ethanodiolate, and I'm going to scale. You don't get the scaling factor, the scaling mark twice, you'll get it once for both of these two. If you found the moles of the hydroxide, used the ratio to find the moles of the ethanodiolate, you've now got 5 marks out of 8 without knowing what you're doing. You can have no idea what you're doing in terms of getting to the end of this calculation, and you can still get 5 marks here. Okay, which is why I emphasize, and I'll say it again and again and again, no blank calculations. You can find the moles, you can get some marks. Moles, ratio, moles, moles, ratio, moles, scale, and you've got some marks even if you don't know what you're going to do at the end. Okay, this is an 8-mark question from a past exam question. Okay, so this is a real past exam question. Okay, and typically in your A-level exams, you will get like one big crazy looking calculation in a paper worth 7 or 8 marks. Okay, Liam, we know that because from looking at the equations, the first equation tells us the manganate is telling us the moles of the ethanodiolate because that's what it's reacting with. And both of our species that we're told about at the beginning have that ion. So it's telling us about both. Whereas if we look at the second equation, the hydroxide is only reacting with the H2C2O4, so just one of them. So if we take the total away from the one that's just one, that tells us how much of the other thing we've got. Okay. Ooh. We are way over time already. Do we want to do another crazy titrations session next week? Yes, I am. Those 8 marks are well deserved. Do we want to do another one? Yeah? Amazing. In that case, next week, we'll be back. Time to be confirmed, but probably the same time, okay? Probably, will it be the same time? I'll confirm it. So make sure that you're following me on TikTok and on Instagram, well, particularly TikTok, because I'll always post a TikTok and also a story a couple of days before to let you know the timing for these lives. Okay, but if you think this was bad, I have a horrific one next. Oh my gosh, it's so good. Okay, so next week we'll continue with these crazy calculations. Indeed, you are here. I love that. Yes, indeed, so these are redox titrations. Okay, yes, Aisha, I've got lives every single week. It's just a question of what topics we're doing. But next week, I think let's stick with our crazy calculations. Okay, and then we'll move on to something else the following week. Okay, for now, have a wonderful evening, a great weekend. If you're on the MES courses, I'll see you next week in our lessons. If you're not, then I'll see you in our live next week, Friday. Okay, bye, bye, bye. Bye.